if I got that first part of that. Okay, so is Q a function of T is our question.
Yes.
Yes. And how do you know that? So how would you explain or justify? Exactly. No repeating T values, yeah. So remember, when we have a table of values, when we have a function given numerically, then we look at the values of the independent variable, and if none of them are repeated, then we know that each input is going to be paired with exactly one output. So yes, it's going to be a function. Okay, then the next question is, we're going to say, is Q linear? And how are we going to justify that? So how do we do that? What's the plan?
Find the rate of change between points.
Yeah, so you got to look at different rates of change. So we have to compare the rates of changes. That's our strategy. And so that means we're going to look at the various, I'm going to call these delta Q over delta T's. That is the change in Q over the change in T. And we can see what that is. So here we're going to take the 150 minus the 50. You with me there? And then I'm going to take the 4 minus 0. And so the 150 minus the 50 is 100. And 4 minus 0 is 4. And simplify. We're taking notes, right? Okay. And 100 divided by 4 is 25. So we've got a rate of change between those 2 points is going to be 25. So if we look at another one, so maybe let's pair these two up. And so now we're going to look at, again, delta Q over delta T. So we're going to check out the rate of change between a couple of different points on this same curve. So the delta Q this time is going to be the 250 minus 150 and the 8 minus 4. And that's going to, again, give us 100 over 4, which is, again, 25. And maybe let's just do one more to be convinced. So if we pick out, say, these two and get a delta Q over a delta T of 350 minus 250 over 12 minus 8, again, 100 over 4, again, 25. So then this is like our litmus test for whether this is linear or not. Because all these rates of changes are the same, then we can definitively say that yes, Q is a linear function of T. And if I'm going to ask the question why, or how do you know, and then what we will do is, because we have shown the work that leads to that, we've demonstrated that, we can say that that's because the rates of changes are equal. They're all the same. Make sense? Let's try another one. And so this time our table is going to be x's and y's. So we'll go x and y. And the x values are going to be 0, 1, 3, 6. 0, 1, 3, 6. And the y values are going to be 10, 40, 70, 30. 70, 100, sorry. 10, 40, 70, 100. So I should have left the other table up there because sometimes what people will say, let me see if I can recreate it real quick. So we had before with the T's and the Q's, we had 50, 150, 250, and 350, and it was 0, 4, 8, and 12. So sometimes people will say, and their thinking is kind of right, but not always, they'll say, well, because the Q values go up by the same each time, that's how we can tell that it's linear. But that's not enough, right? Because here we can see that they're going up by 30 each time. The Y values are increasing by 30 each time. But the X values are not, right? And so that's the part that is going to determine that it's not linear. So is y linear? And the answer is going to be no, so that's correct, it is not. And why is going to be the question. So if it's not linear, that means that every rate of change, the average rate of change between every pair of points is not the same. So to show something is not true, all we have to do is find two rates of changes that are not the same, and then we're done. So on the other one, we did like 3, we did many more to try to convince ourselves that it was true. But to show that it's not true, we can just come up with a couple that aren't. So one rate of change would be, say, the 40 minus the 10 over the 1 minus 0. You with me here? And so the 40 minus 10 is going to be 30 over 1. And so the rate of change between x equals 0 and x equals 1 is going to be 30. But if we look at, say, the rate of change on the next pair of points, so our next rate of change, if we take the 70 minus 40 over 3 minus 1, so as before, because the y values are going up by the same each time, that's going to again be 30, but as Aaron noted, the change in x's is not uniform, is not the same. So now we're going to get a 2 in the denominator, and because these two rates of changes are not the same, that's a convincing argument that this is not linear. Make sense? Okay. So let's change the game a little bit and do some of what we would have called verbal representations. And I'm going to give you a description of a scenario, and then let's see what we can do with that. So suppose that enrollment, which we will call capital E, that's Laramie High School, is 1,000 and is growing by 50 students each year. For the next 10 years, we'll say. Probably not forever. So I'm going to ask you some questions. What is the average rate of change, ROC, and is enrollment a linear function of time? That's our second question. And finally, can you write a formula for the enrollment E? And feel free to consult and collaborate. Talking with somebody within your 6-foot circle is encouraged. Difficult to get anybody to say anything. What's the average rate of change?
50.
Okay, you see that? It's going to be 50. Okay. And is enrollment a linear function of time?
Yeah.
Yes. Okay, convince me. Why?
Because there's a
Because it's
certain.
growing by a constant rate.
Yeah, the rate of change is constant. Is that what you're going to say too? Yes, so since our rate of change is constant, it's 50 each year, then it's going to be linear. So I'm going to say because the rate of change is constant, always 50. Good. Okay, could you come up with a formula? Somebody that hasn't spoken in the last couple questions, so we can get that one, okay?
E equals 50t plus 1,000.
50t plus 1,000. What do you think? Agreement? Thumbs up, thumbs down? Yeah, very good. Okay, good. And so we didn't really say this, but I am playing on something you know. So the y equals mx plus b. That's slope-intercept form of a line. And it sounds like you guys all remember that from your Algebra 2 days, which is good. So that's what we were employing here, is that the average rate of change is our slope. So that's an equality. Those are equivalent to each other. And then our starting value, how much we had when time is 0 for us, is going to be our y-intercept. Very good. So let's try another problem. So let's talk about depreciation here. So suppose a business buys $20,000 in new computer equipment. Buys $20,000 in new computer equipment. For tax purposes, it depreciates to 0 at a constant rate over 5 years. At a constant rate over 5 years. So we're going to ask the question again, can we figure out what is the rate of change? Should we do, maybe we can make a table of values, and then can we find a formula for that? So we understand what depreciation is and how that works.
Mm-hmm.
So, you know, people like to say when you like to buy a car, as soon as you drive it off the lot, it's worth less. So it usually depreciation, the value of something, just depreciates. It becomes worth less over time. It's usually exponential. So it's not typically linear. So when you buy your car, you know, it's worth whatever you paid for it. And then it, over time, becomes worth less and less, hopefully never worth 0. So it has some kind of asymptote or something it's approximating there. Except I'm told that once it gets to be 30 years old, it becomes an antique. And now it starts to appreciate in value. I'll have to show you my truck at some point in time. It's older than you. It's over 30 years old. So I'm going to hold on to it. It's going to grow in value. This is my plan. This is my retirement plan until I can sell it for a fortune and retire.
What kind of truck is it?
It's a 1986 Toyota 2-wheel drive truck. It's in the shop right now, sadly. But it's gaining value, I'm sure. Okay, anyway, I digress. So I'll let you look at this.
To go like a street car.
Yeah, I know. We'll have to take a field trip, yes. I'll bring it out here, and then it might be out here for a long time. I can't get it started again. Okay. Give me a moment. You can compare your answers with somebody in your neighborhood.
Did you get it yet?
I'm still ready.
Okay.
So it's going to be linear. So even though the value of something actually depreciates exponentially, a lot of times if it's a business expense or something, it's depreciated linearly. So you say, you know, you paid this much for it. It's only going to be good, you know, current and useful for you decide the time, 5 years, 10 years, whatever. And so then for tax purposes, businesses will say, well, we're going to assume that it depreciates linearly. And so then they can, you know, use that as a deduction, you know, how much value it lost each year until it zeroes out. And then theoretically, they would have to replace it with something new and the process starts over again. So even though in actuality it probably isn't linear, for tax purposes it usually is. So our rate of change, if we think of that at time zero when we bought it, it was worth 20,000. Then in 5 years, when we have depreciated this out, it's going to be worth 0. And so then our rate of change is going to be a slope. So here we are again, y2 minus y1 over x2 minus x1. And so we're going to get that 20,000 minus 0 over 0 minus 5. So that's going to be a 20,000 over a negative 5 in the denominator. And so 5 goes into 24 times, and then we got 3 more zeros, and we have a positive divided by a negative. So that is going to make our rate of change a negative 4,000. Make sense? What would the units be on this?
Dollars per year.
Dollars per year, exactly. So it is, we are saying it is decreasing in value at $4,000 per year. Make sense? So should we make a quick table of values here? I got to stay in the camera range here. So I'm going to destroy this. Hope we don't need it any longer. So let's do a table here. And so we can say years since we bought it and value in dollars there. So at time 0, this was worth 20,000. So after 1 year, it's going to depreciate by 4,000. So its value is going to be 16,000. And after 2 years, it's going to drop another 4,000 in value. So now we're down to 12,000. See how the game is played? No, I'm running out of room here. And so down another 4, I think will be 8. And another 4 is now worth 4,000. And there we are. After 5 years, it's going to be worth 0. That make sense? So what's our formula? Shall we say, what do you want to call it? Y or something?
Y equals negative 4,000.
Negative 4,000. I go x or t, x, and then plus 20,000. Okay, very good. Okay, so what I want to do now is we're going to change gears here a little bit, and I want to just practice some kind of challenging algebra problems here that you may encounter when we get ready for our next test, because I want to make sure your algebra skills are good. So we are going to solve for x. And so we've got 2x minus 3 all over 5 plus x is equal to 5. Now I'm going to have you come to the board here. We have 2, 4, 6, 8. And I think, let's do this. I'm going to not have you use this board, I guess, because then when I post it on YouTube, if I show a student, then I have to do it privately. But if I don't show any of your vulnerable faces on here, then I can do it public. And so I'm going to do that. So one person, you can choose, can come up to the board and grab whatever piece of chalk you would like. and whatever eraser, and you can work on this board, this same problem. 3 others can go to each of the whiteboards there. You can grab a marker and an eraser. Okay. Now, once you grab that, take it back with you to your desk because you get to use it for the whole period. And we'll get the other group that doesn't, well, we can maybe do this. Might have enough markers and erasers, we can all do this. And we'll try to alternate as we do different problems. So as you go up there, as you go up to the board, my goal, remember, is for you to collaborate. Remember that the best learning happens when you discuss, so you can talk about the problems, and you have talked so well already this morning. That was sarcasm. I'm not sure if they're picking that up on the video, but you can talk to each other as you do this. You can look and compare, and the poor Lone Ranger up here by themselves at the board, you can collaborate with people that are also working at their desk, so you got to help her out and make sure that you're agreeing, or if she gets stuck or whatever, or you get stuck, you got to have that discussion and dialogue. And if somebody gets stuck, then you can teach that person socially distanced from 6 feet and get the best learning experience of all. Does that make sense? Are we ready to volunteer voluntarily, or do I need to volunteer people to come up to the board first? Ready, set, go. Oh, I like that. Nice. Okay, so if you're at your desk, you're doing it in your notes, but we're going to have, so Jesse and Heidi, you guys can kind of be on the same team here with Erin. So you compare what you're doing with her and give her feedback. You guys can dialogue between each other. And
Is there another marker?
yeah, those not good. Okay. Just throw that out. If there's one that doesn't work, you've never happened with chalk. And they're, I haven't used all summer, so if you get one that doesn't work, just pitch it and keep going until you get one that's not going to aggravate you. What do you think? Check with those guys.
Anything that can you read that in here? There's a chapter 4.
Need your binoculars.
Sorry, my hand is so small.
And so when you're at the board, if once you're finished, don't just go sit down. Check with your board mates up there, the people that are up there with you, and make sure everybody is getting the same answer and that they agree. So,
Gentlemen, again.
oh, well done, well done.
Is this 6 feet long? You can think of this as close as possible.
I thought
My
we
arms are
could.
about 6 feet long.
Yeah, I thought we could fit 3 groups up there, but then I think the middle person would be like, stuck right there
I
on
do
the
like
seam.
that.
Okay, cool. I am doing it right.
Oh.
I'm just gonna, as you're finishing up, go ahead, if you haven't already, I'm gonna work it, because this is gonna be on the video too. So we want to get rid of the 5 in the denominator. So we're gonna multiply through everything by 5. When we multiply this fraction by 5, those are gonna cancel, and we'll just get the 2x minus 3. This x has nothing to cancel, so it's gonna become a 5x. The other side of the equal sign also gets multiplied by the 5 and becomes 25. Now it looks more routine. 2x plus 5x is 7x. We're going to add the 3 to the other side to make that 28. And then we divide by the 7. So I think we're trying to get 4.
You good back there with that? Nisha mixes up.
Oh, I have to
like
add,
we should have some fraction.
Okay?
Yeah.
We good now?
Yeah, I
Get-
can't read my own handwriting.
Always a challenge. I can relate to that. Okay?
You don't know
Okay,
what's-
you guys can go ahead and erase what you got up there. Take your seat. Keep your marker or piece of chalk with you.
Are we gonna do more?
Oh yeah, well, you want to do it? We can stay up.
We should
Well,
do some more.
do some more, or should we bring them up? Is my question. What do you think? Let's try because it gets old sitting down all the time. So keep your piece of chalk or marker with you, an eraser, and then the next group is going to come up and try the next problem, which is going to be this is a challenging one too. Solve for y. So if you need some help along, we maybe talk strategy here too. 3x
If you really don't want to go.
plus xy is equal to y minus 7. No, liking isn't it? It's an opportunity to participate in classroom activities here. Okay, if you weren't at the board last time you are, you can pick chalkboard or whiteboard. Oh, and the slow one gets the chalkboard. It's like that, is it, huh, Jesse? Slide over a bit if you would, thanks you. I know, it is the best. Now we're trying to solve for y here. You will notice that there are two different terms that have y in them. This is what makes this challenging. Does anybody have an idea how we will proceed here? What's our strategy going to be?
Get x on one side and y on the other.
So let's get all the terms with y that we're trying to solve for on one side of the equal sign, whichever one you want, and the terms that don't have y go to the opposite side. So y's go on one side. Any term that's got a y in it goes on one side. Any term that doesn't have a y on it has to go to the other side of the equal sign. Need a marker, Jesse? I don't know if they use it last summer, so if one doesn't work, just throw it out and get one that is going to not drive you crazy. Now, once you get the y's on one side of the equal sign, what's the strategy next?
Divide by y.
No, not quite. Instead of dividing by it, we want to
Factor it out.
factor it out. So once you get y's on one side of the equal sign and everything without a y on the other side of the equal sign, factor that y out. It doesn't matter which side you go. We'll see there in a moment.
You get 3x plus 7. Yeah.
And then once you have factored out the y, what do you do?
Divide it.
Divide. Yep. So depending which way you went with the y's, you may get one version or the other. So we're going to factor that y out. And so when you factor this y out, what's left is x plus 1. Okay. You see what we got here. How are you doing? You're doing that great. Yes,
That's final answer? Like,
Yeah.
did you pick kind of like,
that is. Okay. In good shape.
yeah.
And so you were great.
Follow the
today,
same
which is good. Now factor the y out. So you added the 7 here. And we're doing a little bit of made up math here. So if you divide by x, you know, yeah. Well, yeah, and then you have to divide this by that also. So this stuff is not correct. Okay?
Tuesday.
That's not okay. All right, you good to go? Okay, Jesse, can you check on Colin's work there, make sure he's okay to go? Colby, I'm sorry. Colin sits in that place in the other class. Colby, thank you. Yeah. Okay, so Jesse hanging there with Colby till he's finished. Everybody else can take their seat because I'm trying to hustle. Take it with you. So when you're finished, what you're going to do is there the used chalk and erasers will go here, and the used markers and erasers will go here. But not till the end of class, because I may get you up there again before we're done, is my hope. Okay? Okay, as they're finishing up, the first group is going to come up here, and we're going to solve Again, solving for x. X squared plus 3x is equal to x plus 6. Again, solve for x. So anybody have an idea as they do this, as they get started, what our strategy is going to be?
Get all the x's on one side.
Okay, good. And remember, you notice you got an x squared here. That's the new twist on this. So in general, when you have something with an x squared, what is our strategy going to be?
Quadratic formula.
Well, we can do that, but that's kind of like, using that sledgehammer to crack open that peanut. That's a kind of our strategy of last resort. What's our first choice? Factor, factor, factor. Ah, the Box and Diamond crew. Get the rust off, because we have to be able to
Oh, that's
factor.
all right.
Jesse and Heidi, you're looking up occasionally at Aaron's work with your binoculars, right?
Sorry, I tried to write a little bigger this time.
Colby, you can talk to Cade too. It's got to be equal to 0. You got to make it equal to 0 first. Don't factor before then, or it's not meaning. It won't have good meaning. So you can't factor when it's equal to 6. You got to factor it when you subtract the 6 over and make it to 0. Because we want two things to be that multiply to be 0. Two things that multiply to be 6, there's an infinite number of possibilities. But if two things multiply to be 0, one of them must be 0. Oh, that one there. Looks like it isn't going to factor, huh?
No, it's
Oh,
not.
Aaron was right in the
I was
first
like,
place.
wait, it's not. Why
Oh,
is it
dang it
working?
anyway. I
Do
guess
I
we're-
not know what multiplies to 6?
You're going to have to use quadratic formula after all, because it doesn't factor.
Negative b plus
Man,
the square.
You made this problem up.
Of b squared minus 4. A
Yeah, who could forget the quadratic formula?
all over 2
Nice.
times that.
Okay, we got saved by the bell. We'll come back to
I was
this.
right, though.
You were right. You were right.
Because I was like, I was sitting there, I was like, wait, what multiplies to 6? I could not figure it out. So I had to know.
Yep. So you put your use markers and erasers in there. But you did your math here.
Yeah, no, I tried to talk to my teachers. I was like,